Bismillahirrahmanirrahim. Assalamualaikum, brothers and sisters. Today's episode is a revisit the first law of thermodynamics, focusing on the heat capacity of an ideal gas. How do we determine the internal energy change of a quantity of argon gas given its heat capacity at constant volume, Cv, and at constant pressure, Cp, if the pressure changes or if it remains constant, while the temperature and the volume do change? Join me till the end of this video. Watch and learn. The problem is a quantity of argon gas whose molar heat capacity at constant volume equals 3 halves times big R, and its molar heat capacity at constant pressure equals 5 halves times big R. The gas is at pressure P equals 1.20 times 10 to the fifth power Pascal and occupies a volume V equals 0.250 cubic meters. Calculate the change in internal energy of the gas if the final pressure and volume of the gas are, letter A, the pressure P is equal to 2.40 times 10 to the fifth power Pascal, while the volume V equals 0.250 meter cube. Letter B, if the pressure P equals 1.20 times 10 to the fifth power Pascal, and the volume V equals 0.125 meter cube. Letter C, if the final pressure P2 equals 1.80 times 10 to the fifth power Pascal, while the final volume equals 0.600 cubic meters. So we are given the following data. The heat capacity or molar heat capacity, capital C sub V, equals 3 halves times the universal gas constant, or big R, while the molar heat capacity at constant pressure equals 5 halves times big R, where uh, capital R here is known as the universal gas constant, equals 8.314 joules per mole Kelvin. Also, we are given the initial pressure P1 equal to 1.20 times 10 to the fifth power Pascal. And the gas occupies an initial volume V1 equal to 0.250 meter cube. The target variable in this problem is the change in the internal energy, denoted by delta capital U. Given the following conditions, if the final pressure and the volume of the gas are, in part A, the pressure P2 equals 2.40 times 10 to the fifth power Pascal, while the final volume is equal to 0.250 cubic meters. In part B, the conditions are if the pressure P2 equals 1.20 times 10 to the fifth power Pascal, while the final volume V2 equals 0.250 cubic meters. And in part C, the conditions are if the pressure P2 equals 1.80 times 10 to the fifth power Pascal, while the volume V2 equals 0.600 cubic meters. Capital C sub V refers to the molar heat capacity of the gas at constant volume. In figure 1a, the method of measuring this molar heat capacity at constant volume is illustrated. Okay, and moles of the ideal gas, such as argon, is placed in a container, all right, of fixed volume, and an infinitesimal amount of heat dq is added to the system, right? And it is equal to the product of small n, the value of uh, molar heat capacity at constant volume, and uh, the infinitesimal change in temperature, or the T, keeping the volume constant, which is a process, okay, known as isochoric thermodynamic process. Capital Cp, on the other hand, refers to the molar heat capacity of the gas at constant pressure, right? And how it is measured is also illustrated in part B of the figure, where the container here has a movable piston that applies constant pressure, a process known as isobaric process, right? The infinitesimal heat dq is added to the system at constant pressure and is equal to the product of small n, uh, the molar heat capacity of the gas at constant pressure, and the infinitesimal change in temperature. And for a specific ideal gas, the value of the molar heat capacity at constant pressure, or Cp, is greater than the molar heat capacity at constant volume, and their difference is no less than the universal gas constant, or big R. Before deriving the formula for the change in internal energy delta U of argon in this problem, let us first analyze the pressure volume graph shown in figure 2, which shows some examples of thermodynamic processes. The first one is uh, When the volume of the gas increases from V1, okay, to V2, right, at constant pressure P1. So we call this an isobaric expansion of the gas. And it suggests that there is work done by the system or by the gas on its surrounding. And the area of the shaded rectangle represents such a positive work, right? So, following the first law of thermodynamics, the amount of heat Q added to the system is equal to the internal energy change delta U plus the work done W, all right? Work done by the system. The other process shown in this PV graph is when the pressure increases from P1 to P2 without, all right, changing the volume of the gas, right? So since there is no change in the volume, which we consider as an isochoric process, right? We say that the work done is equal to zero. And again, based on the first law of thermodynamics, if the work done W is equal to zero, then it follows that the heat big Q, okay, that is supplied to the system is just equal to the change in the internal energy of the system or the gas. So, moving on now to our equation for the change in internal energy of the argon gas, right? Denoted by delta capital U. So, it is just equal to the product of small n, which is the number of moles of the argon gas, and the molar heat, all right, at constant volume, and then multiplied by the change in temperature delta capital T. Take note, all right, in the process that we are analyzing, uh, which is the case of the argon gas, the temperature change, right, from T1 to T2, right, corresponds also to a change in the internal energy, okay, capital U1 to capital U2, right? And our goal is to find a direct formula for determining delta U, right, in terms of the heat capacity of argon at constant volume, the initial pressure P1, and the initial volume V1, as well as the final pressure P2 and the final volume P2. Unfortunately, uh, neither the number of moles small n of the argon gas nor the change in temperature delta T, okay, is given, right? So we have to include another equation, the ideal gas equation of state, right? Uh, the pressure P times the volume B equals small n times big R and the temperature T, right? And together with the definition of uh, the heat capacity at a constant volume, okay, they will be our basis for our derivation. So, uh, delta U or N Cv delta T, okay, can now be expressed as uh, the heat capacity at constant volume or Cv divided by the big R and multiplied by small n times big R times delta T, right? So we are now talking about change in temperature delta T. So our ideal gas law, okay, is now modified. Instead of just the temperature capital T, right? We'll be using delta T. And since the product of small n, big R delta T, okay, can in fact be replaced by the change in the pressure P times the volume V, or delta P times V, okay, which is of course the same as the product of the final pressure times the final volume P2 V2 minus, okay, the product of the initial pressure P1 multiplied by the initial volume V1. So our equation for delta capital U, okay, can now be expressed as uh, Cv, or the molar heat capacity at constant volume divided by the big R, all right, and multiplied by quantity P2 V2 minus P1 V1, right? So from here, we just replace small n times R delta T by quantity P2 V2 minus P1 V1. And since the value of the molar heat capacity at constant volume is given in the problem equal to 3 halves times big R, right? So if we substitute this here, uh, we'll be able to cancel out big R and come up with our desired formula for determining the change in internal energy, or delta U, which is equal to 3 halves, all right, multiplied by uh, the product of the final pressure P2 and the final volume V2 minus the product of the initial pressure P1 and the initial volume V1, right? So this is the desired formula or equation that we want, because all these variables P2, B2, P1, B1 are uh, given in the problem. Moving on now to our computations, uh, using this formula to determine the change in the internal energy, delta U, which is equal to 3 halves multiplied by P2 V2 minus P1 V1. So in part A, delta U is just equal to 3 halves multiplied by 2.40 times 10 to the p power Pascal times V2, which is 0.250 meter cube, and then minus the product of the initial pressure P1, 1.20 times 10 to the p Pascal, multiplied by the initial volume B1, 0.250 meter cube. So when we do our math, we are able to simplify this equation now. So delta U is equal to 3 halves times quantity 0.6 times 10 to the p power joules minus 0.300 times 10 to the p power joules. And finally, we get the amount of the change in the internal energy delta U equal to positive 4.50 times 10 to the fourth power joules in 3 significant figures. We are emphasizing that uh, the internal energy of the system or the argon gas, okay, is increased. Hence, we have here the positive sign. Okay, the internal energy of the system increases by this much, 4.50 times 10 to the fourth power joules. Following the same formula, in part B, the amount of delta U equals 3 halves multiplied by uh, the product of P2 and V2, or 1.20 times 10 to the p power Pascal uh, times 0.125 meter cube minus uh, P1, 1.20 times 10 to the p Pascal times V1, 0.250 meter cube. So again, doing our math, we have this simplified equation. Delta U equals 3 halves multiplied by quantity 0.150 times 10 to the fifth joules minus 0.300 times 10 to the fifth joules. So we finally get the amount of the change in internal energy, delta U, equal to negative 2.25 times 10 to the fifth power joules, also rounded to 3 significant figures. All right. The minus sign here suggests that uh, the internal energy of the system has been decreased by as much as 2.25 times 10 to the fifth joules. And lastly, computing for delta U in part C, we have delta U equals 3 halves times 1.80 times 10 to the p power Pascal. That's the final pressure P2, and multiplied also by the final volume 0.600 meter cube, and then minus the product of P1, 1.20 times 10 to the fifth Pascal, and V1, 0.250 meter cube. So again, when we do our math, our equation reduces to delta U equals 3 halves multiplied by quantity 1.08 times 10 to the fifth power joules minus 0.300 times 10 to the fifth joules. And finally, we arrive at the amount of change in the internal energy delta U equal to positive 1.17 times 10 to the fifth power joules, also rounded to 3 significant figures. Then again, the positive sign here implies that the internal energy of the system has been increased by an amount of 1.17 times 10 to the fifth joules. So just before we end, let us reiterate the key concept applied in this problem. When small n moles of an ideal gas undergo a thermodynamic process in which the temperature changes by delta T, the change in internal energy is equal to the product of the number of moles small n, the change in temperature delta capital T, and the molar heat capacity at constant volume C sub V. That is, delta U is equal to the product of small n, C sub V, and delta T. This is true whether or not the volume of the system remains constant. So on this note, may I say mabuhay. Till the next upload, mashallah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel. Alhamdulillah.